Alright, so this is going to be a pre-recorded video because I might need to step away from the keyboard um, when the electricians show up, for a inspection of the breaker panel that they installed a few weeks ago. So I might need to step away, and when I do step away, you guys can watch the solution of the lab that was due this morning. All right, so let's go ahead and just do the entire lab, and we'll start from question 1. When the function returns a scalar type, what is the mechanism in the context of this class? And the question is, the answer is register A. So click on next. Next question, how are parameters passed from a caller to a subroutine? So when you compare all of these options, there are specific ones that I said, it won't work in class, such as in registers A, B, and C. On the stack above with high address than the return address, that is the correct answer. But we'll check out the other ones too. In special parameter registers, such as the instruction register is not a it's not a special parameter register. We never talked about it that way. On the stack below the return address, that is not the case, because the caller has to push the parameters before the return address, and that is part of the agreement. And as a result, it is not below; it is actually above the where the return address is on the stack. Next. So here is the Fibonacci code. Here's main, and this is function f, and the question mark is for you to specify a value to evaluate. So the question is function f recursive? And you got a few answers here, possible answers. The answer is yes, it is recursive. It does not depend on whether it's in f or main, because recursiveness refers to whether a subroutine calls itself or not. But so you have to look into the definition of the subroutine, and in this case the subroutine does call itself, and as a result it is recursive. Alright, so click next. And I believe this is the last of the questions. This is question number 4, and it's worth 4 points because you have to turn in your actual program. So you need to implement the C program corresponding to the code in question number 3 and test it, and then just kind of work with it. So there are several ways to test this. Okay, so let me just go back to the previous question here. As far as main is concerned, you don't have to implement main exactly the way it is. So if you don't want to use a local variable to store the return value, you can just call the function without storing the value. So that would be the easiest way to implement main, because we have the trace analyzer. And even without the trace analyzer, you can always run Logisim in GUI mode and just examine register A after the subroutine returns. That would also tell you whether it has the right value or not. So main can be really, really simple. The complexity is not from main, but from the subroutine itself. So what I'll do is I am going to copy and paste this code into assembly code. Okay, so I'm just copy it first here, and then we switch to my text terminal. And I have Logisim running right now. I'll just kind of stop that from running because I don't need it right away. And let's go ahead and take a look at this code. So we'll look at the C program on one side. So this is where the C program is going to be. And let me paste it here. All right. So we'll take a look at f.c, which is the C code, and then f.ttpasm, which is the assembly code. The C code is here, and obviously we have to replace the question mark with something that can be tested. Okay, so let's say 4. Okay, that's going to take a while already because of the way this function is recursive. It is almost exponential. In other words, if you say f of 5, it would take almost twice as long as f of 4. So it does take a little bit of time. All right, so on this side we have the assembly code. So we have a usual no op, because if I want to test this code in the using the trace analyzer, this will give me the option to do it. JMPI, or if you want to, you can always load the stack pointer with a 0, and then we have a JMPI to main to skip over the definition of f. So this is just the way I do it. You don't have to do it this way, but whatever you do, your f as a subroutine has to be self-contained. So this way I can extract the definition of f and be able to test it using a main that I am going to write. Okay, or yeah. So I'm going to use my main to test your f, the subroutine f. So f is going to be here, and then main is going to be here. So I'm going to do the full version of this program, so that main has a local variable. So the local variable of main, which is x, is exactly where the stack point is pointing to, simply because main has no caller. And if it doesn't have a caller, it doesn't have a return address on the stack, nor parameters. So x is basically exactly where the stack point is going to be pointing at. And the main local var size is x1 plus. So this x is what is the last local variable, and x being the only local variable is the last local variable. This 1 refers to the size or the number of bytes of the last local variable that is on the stack. So when we add these two, it becomes the number of bytes that all the local variables are going to take. And then I highly encourage people to use a template, okay, which is LDI a main local var size, and then do a subtraction, so that this way we allocate the stack space for local variables, and then we do something similar, except this time is add, to deallocate all the local variables, or the space that has been used up by the local variables. So I encourage people doing it this way simply because this works regardless of how many bytes are being used for local variables. It can be 0, okay? If it's 0, we just wasted 4 instructions doing absolutely nothing, but it's not wrong. It can be 1, which could have been done using a decrement and an increment, but once again, this is just not efficient, but it is not wrong either. We can have a bunch of local variables, in which case this approach also works. Okay, so now we are into the actual main subroutine. The first thing we want to do is to call f with an argument of 4. So let's do that. Okay, allocate the space for the argument. Store that to the location that we just allocated. So this is going to push the 4 on the stack, and then we have decrement d LDI a dot 5 plus. This is how we calculate the return address. Then we still have to push it on the stack. Okay, so there we go. JMPI to f to control execution in the subroutine. And when the subroutine returns, we have to pop, or well, I shouldn't say pop, but we have to deallocate the argument that's still sitting on the stack. So that can be done by just an increment d. That will balance the stack. So at this point, register A is going to have the return value from f, where I need to store it to x. So we need to calculate the address of x, which is LDI bx, add bd, and then do a SDBA. So that will store the return value of f into local variable x. And then we obviously immediately deallocate it because we are already at the end of main. So this is main. And if you want to test main individually, you can do so by making f really simple. So f needs some code that has to be here, which is the return code. So that can be done by using a LD BD, increment D, and JMPB. So these 3 lines of code, okay, let me turn on line numbers. So line 6 to line 8 is going to work for any subroutine because it's not using register A. So if A has something to return, that's fine because it's in register A, and register B is free to be used for this purpose. If F does not return anything, it's still okay because register B is always free. So this is a template. So if you want to test whether your main is working or not, you can do so by just putting an LDIA with whatever value you want it to return, say 51. Okay. Then you can go ahead and assemble the program, run it, either run it through the GUI version, where you can kind of confirm whether it works or not in the GUI version, but it's kind of final, because in the GUI version you can basically stop at the halt instruction. Then you can test whether the stack pointer is back to 0, and you can then see whether location FF has a value of 51 in hexadecimal. So 51 in hexadecimal is 3 times 16 plus 3, so that is a 33 in hexadecimal. So you can test your program that way, and then once you test the program and it works, then you know main is working the way it's supposed to, or more or less, because we are not accessing the parameters. We are ignoring the parameter of 4 at this point, but at least you were able to call f and it returns a value which is then stored into local variable x, and the stack is balanced. Okay, the stack pointer is going back to where it started off with in main. So this is what I mean when I said test your program in steps. Is take baby steps. Just don't write too many lines of code at once. So assuming the program works, so now we can take into account all the stuff that is in F. I will write this code as it is in C. In other words, I'm not allocating an explicit local variable, because one of the points of this particular homework assignment is for you guys to understand how we can use the stack as a temporary place to store values that we need to use later on, instead of using explicit local variables. So you can use explicit local variables in your program, and I will not mark it down for points, but I'm going to demonstrate it without the use of any actual explicit local variables. All right, so it's time to define a bunch of labels. We got n, which is a label, and then we have local variables. So I'm going to define main f underscore local var size, and we'll define it to be 0 because there is absolutely no local variable whatsoever in f, but that's okay. And then in that case, n is just going to be f local var size 1 plus. This 1 here has to do with the return address that is sitting on the stack. And in this case, the stack pointer is going to point to the return address as we execute the body of the subroutine, because we don't have any local variables. So this is how I define all the labels. And once we have all the labels defined, now we can start to implement the code that is in the C program. The first thing we need to do is to see whether n is less than 2 or not. Okay. There's no easy way to test against 2. There's a shortcut to test whether it's 0 or not, but against 2, there's no really special way to do it. Okay, so we have to put n into one of the registers, and then put 2 into the other register, and then use the compare instruction. So we'll go ahead and do that. Okay, so it doesn't matter which one is which one, but it would seem to me that if n is in register A, we might be able to reuse it right away, because you can see how n can be a return value right away. So it might make sense to use register A to store the value of parameter n. So now we do the usual stuff. Okay, so n is really just the offset, so we say add AD, so now it becomes the actual address, and then we do a LD, because we are reading, we are not overwriting that value. So at this point, A does have the value of n, and I'm intentionally not writing any comments because I want this to be an exercise for you to write down the comments. Okay, I'll give you some suggested activity after talking about this. So now that we have register A with n, register A has the value of parameter n. Now we use register B or C, doesn't matter which one, to hold the value of 2, and now we can compare. So now the question is, how are you going to compare this, right? So the decision point is whether n is less than 2 or not. And we do have a bunch of conditional branch instructions that will branch if and only if only if the minuend is less than the subtrahend. So that means it is better to test A versus B, or to execute A minus B instead of B minus A. Now B minus A is going to work too, but you will need multiple conditional statements because in that case you'll be testing whether 2 is greater than or equal to, and greater than or equal to is not less than. So you're going to have to jump through some hoops to get that one to work, which is not worthwhile. So I just do it like this, okay? So if A, which is n, is in fact less than 2, then we can only use a JXI instruction here, depending on the flag, okay? So the question is, which flag is going to indicate that n is in fact less than 2? Then we want to branch to a label and just say, f no recursion, because that's what's going to happen, if A is less than B, if n is less than 2. So we got a few choices here. We look at the 5 flags. Z is out, right? Because because when n equals to 2, we do want to perform recursion. Okay, so that is out. So the only options left are the other 4 flags. One is sign and overflow. Sign and the overflow flag, they are typically not used on their own, especially overflow. And in this case, the sign flag should not be used, okay? Because the sign flag by itself really does not indicate whether the result is whether it's less than or not, even in the signed case, okay? It does not always return the correct value. That is why we have the overflow flag. But the overflow flag by itself is also usually not very helpful, and we need to use the L flag. But the L flag, like this, is only useful when we are performing signed comparison. And since in the C code it is unsigned, we should not use JLI. Now, does it mean JLI is not going to work? The answer is yes and no, because in this case, JLI will work for certain cases of n, but it won't work for certain cases of n also. Now, we want the code to be correct for all cases, so that's why we should not be using L, even though it does work for all practical purposes, okay? But since it is still the wrong thing to use, I will still mark it wrong. Okay, so the correct flag to use is the C flag, which is actually the borrow flag of the subtractor. So that would be the 100% correct flag to use. So I just want to make the point again. If someone is using the JLI instruction, I will mark it down. Okay, even though it may be just a little bit, it will be marked down because it is an incorrect answer. Okay, the fact that it works for certain values of n is, to me, irrelevant, because just because it works in this case doesn't mean it works in all cases. Now, it works in this case only because we only got a stack size that is so big, and we have a recursive definition of the Fibonacci algorithm. But there are ways to do this without using recursion, and as a result, it does not consume space on the stack, and is a whole lot faster as well. So in those cases, then the program is not going to work. It will basically say, it will make the wrong decision and return the wrong value in that case. So we don't want to use a JLI. We really should use a JCI in this case. And I'm just going to nag a little bit more. Programming, I think, is not about whether it works for certain cases or whether it works for the cases where the assignment can test. It is about whether it works in all cases. The mentality of "but it works in this case" is how we got into computer security issues and why programs crash. Because when the program was first written, whoever was writing the program only cared about whether it works in a very specific range of cases or not, but that person did not account for all of the other cases that might happen in the future. So So the mentality of thinking whether it will work, but only in certain cases, whether it will work for the homework assignment or whether it will only work, um, if you're at work, the boss may say, okay, these are some sample values that you can test, and if somebody is to focus on only those cases, those programs will prove to be very unreliable in the long run. And we don't want that to happen. I certainly don't want a software engineer with that mentality to write the firmware of a pacemaker that I might need when I get older. Okay, so I absolutely do not want people to write programs with this kind of mentality. All right, so getting back to here, so F no recursion is a label here. So now the question is, what if I fall through this JCI instruction? Well, if I fall through this instruction, it means n is greater than or equal to 2. So depending on how you want to structure the program, you can put the actual code of recursion here, or you can put it after this label. Okay, so this part is up to you, okay, whether you want to kind of save a JMPI instruction, because, well, actually you'll be saving 2 JMPI instructions, because if you do a JMPI here to F underscore recursion, then you also need a branch around label over here, for J no recursion. So we are just going to say, okay, handle recursive case here. Okay, and then we'll say handle non-recursive case here. Well, as it turns out, the handle non-recursive case is really easy. Absolutely nothing. We don't need to do a single thing, because the non-recursive case is to return the value of n, which is already in register A, the way we set it up. So there's absolutely nothing we need to do here. So we do need F underscore return as a label here, because the handle recursive case, we need to branch to that label. Technically, yes, it can still fall through to F underscore no underscore recursion, but once again, that is dependent, okay? Because it's only because in the no recursion case that we don't have to do a single thing, that falling through is not going to be a problem. So if I want to make sure this code does work, even if I were to later on be able to change this expression, then I will have a branch around JMPI to F underscore return, because I don't want this program to be to stop working just because later on I decided, hey, guess what? For the no recursion case, I got something else to do. Because if I have one single instruction here that will change the value of A, then this program is not going to work the way if I were to write it without line 17, without the unconditional branch around the no recursion case. So I'm going to have a JMPI to F underscore return, even though it is not needed. Okay. All right. So now getting into the actual recursive case, which is F of n minus 1 plus F of n minus 2. On last Thursday, I gave you 2 programs. One is recursion, but without multiple recursion points. This one has quote-unquote multiple recursion points because it's calling itself at 2 different places. So one of the programs that I gave you on Thursday is a program that is simply recursive. And you can see in that particular program, all we have to do is to push the argument call f exactly the usual way, and do something about the result, the return value in register A, and we are done with it, right? So that's the first program. The second program is not recursive, but it has 2 function calls within an expression. Okay, so with that one, I illustrated, how you have to save the value from how you have to save the return value of the first call before you perform the second call, because there's no telling what registers is the second call is going to overwrite. So you cannot assume register A to be the same, or any other registers. So that's one thing that I illustrated on the other day. So what we need to do here is to combine those 2 programs into one single piece of code. So we have to understand that recursion is not special in the sense that we push the argument exactly the same way as before, we perform the call exactly the same way as before, we deallocate the argument exactly the same as before, and we use the return value in register A. Guess what? Exactly the same way as before. Okay. And recursion also does not impact the way that we need to save the return value before we get the return value from the second call, so that we can combine the two return values into one. That part does not change either. Okay, so let's go ahead and write this code then. Register A already has n, so we need to do a decrement A, so the A is now n minus 1. Then we push it on the stack, decrement D, stda. So now we have n minus 1, which is this part here, push on the stack. Now we need to push the return address. The way we perform a call, pushing the return address, JMPI to the subroutine, so that it can come back to the point, the continuation point, it doesn't change whether we are calling the subroutine from itself or from outside of the subroutine. So it's going to be exactly the same, which is decrement D, allocate the space, LDI. We can trash register A because we push it already on the stack. So LDIA with .5 plus stda, and then JMPI to the subroutine. But you're going to say, but it's function f, it's the same subroutine that we're in. Well, then we just do an unconditional branch to f then, right? So calling any subroutine is the same whether it is recursive or not. So when we are back, we just have to increment D, right, to deallocate that 1 byte on the stack that we have used for the argument of f of n minus 1. So now we need to look at register A and go like, I can't reduce register A right away because it is part of an addition, because register A only has this part of the addition. So we can't really do much about A at this point, but I don't want to lose it either. This is where we say, let's go ahead and push register A on the stack. So we decrement D again, and then we stda to push the return value of f of n minus 1. So it is now saved on the stack. And someone's going to say, well, between line 25 and line 27, can't we just kind of comment out both instructions, because first incrementing and then decrementing D doesn't really do a single thing to register D? The answer is yes. Okay, we can actually comment out line 25 and line 27 at the same time, so that register D is remaining unchanged. In other words, we are simply overwriting in that case on the stack what used to be the argument of f of n minus 1 is now quote-unquote repurposed to the return value of f of n minus 1. I could have done it that way, but procedurally speaking, we are actually deallocating it first to finish the call, and then we push the return value back on the stack because we need to do that. Okay, so conceptually, I'm leaving line 25 and line 27 in the program, even though when we run the program, they can be they cancel out each other. And then someone is going to ask, but isn't this violating your principle of this is a special optimization that only works sometimes? Well, it does work all the time. It doesn't work only sometimes. This one does work all the time. It doesn't depend on what the value of n is. As long as the structure of the expression is this, it still works. Okay, so it's not a special case where the program is not going to work in some other cases. All right, so now we look at so now that the return value of f of n minus 1 is safely tucked away on the stack, now we can call f of n minus 2. Somebody's going to say, well, it wouldn't be a nice thing to retrieve n minus 1 on the stack so that we can reuse it down here? We just have to decrement it one more time. The answer is no, because a subroutine can change the way this particular subroutine is defined. N is not a const, so f could have changed the parameter on the stack. So when we retrieve it, it would have been a different value from the invocation that we just returned from. So we cannot actually reuse it. I mean, that would not be the correct thing to do. So the correct thing to do is to get it again from the current invocation. So we do LDI AN add AD so that we and then also LDAA. So we are retrieving n back from our own frame. Okay, we're not relying on the frame of the invocation that we just came back from. Okay, and this time we have to decrement it twice. So decrement A, decrement A. So now register A is n minus 2. But here is the problem, okay, is this expression n is not going to work because n is an offset. It's an offset from where the stack pointer points to where n is in the frame of this particular invocation. But that offset is calculated at the entry point of the subroutine. It is not calculated based on here because we just pushed something on the stack. So the stack pointer is now actually pointing to one location lower than where it's pointing to at the entry point of the subroutine. So that offset is now one byte short of finding the actual parameter n, and this is where we need the n1 plus in order to compensate for that. Okay, and as a result, so this will work. Okay, your n1 plus is going to work, and I think on last Thursday I illustrated this as well with the last program that I ran. I illustrated this because I think I turned Ryan to be parameterized, and as a result, when I call Ryan after saving the return value of Johnny, we needed to use the same technique. Okay, so so I actually illustrated 2.5 programs on last Thursday. Each one is relevant to what we are doing in this particular program. All right, so now that A is n minus 2, we can perform the call. We can push it on the stack first. So we have decrement D, stda to push it on the stack. And then we're gonna have the return address to push on the stack. So we decrement D, LDI, A dot 5 plus, and do a stda. So this pushes the return address on the stack. Then we perform the jump, which is going back to label F because we're calling subroutine F. And somebody's going to say, but this is the second time we do it. Don't we need to do something special about the return address? Well, we just did, because this .5 plus is going to give register A a different value compared to this particular .5 plus. The dot is representing the address of the instruction where the dot is on. So the address of this particular LDI instruction, this one here, is different from the address of this particular LDI instruction. So it's already taken into consideration. When the second invocation f of n minus 2 returns, we do the same thing. Okay, we have to increment D to deallocate the argument. And now we got one thing extra on the stack, which is the return value of the first call to f, which is the return value of f of n minus 1 that is still sitting on the stack. So let's pop it, right? So let's get it into register B because I don't want to put it back into register A. Register A now has the return value of f of n minus 2. So we pop the return value of f of n minus 1 into register B, and don't forget to increment the stack pointer because this is how we pop. Okay, because pop is not just retrieving the value, it is also freeing or deallocating the location that had that value. So now the stack is quote-unquote balanced again, and now we can perform the add instruction. And add AB makes more sense than add BA because we want to add we want the result to be in register A so that it is already in the correct register for returning the value. So now we do a JMPI to F return, which is here, which is really just a return code. So that should do it unless I make some stupid mistake. When I'm doing this, I'm not actually copying from some other program, that's somewhere else on the screen. I'm actually working on this from scratch. All right, so let's give this a try and see if it works. And my hope is that it does not work so that we can actually do some debugging. But if it does work, hey, I'm not going to complain either. All right, so let's do a cat.ttpasm to xclip cell clip. and then we go back to the assembler. All right, so do I have the assembler? Yep. Okay. This is why I like vertical tabs, because I can actually see the entire thing. And we go back to the source tab over here. Oh wait, I can't do it here because this one is still being shared to the class, because I'm doing this before it's due, so I probably want to make a copy of this first. So we'll go ahead and make a copy. And this is going to be a private version. Then I have to move it somewhere outside of the shared folder so that people cannot see it. So we'll go ahead and move it. There we go. Let's see. Let's just move it to the folder that is specific to the summer session. And I'll just stash it here for now. There we go. So now people cannot see it. Alright, so let's remove all the instructions and then paste the new program in and make sure that we don't have an error. Okay, no errors, that's all good. And then we download it as a CSV, and I'll just call this f.csv, and I go back to my command line and run it. So I'm going to go back to this one and then specify dash tty table dash load f.csv, and then redirect to f.tsv. And it's going to take, okay, it's not taking that long. Okay, that's actually reasonably fast. So we'll go take a look at the execution of this program in the trace analyzer. So the trace analyzer is here. There we go. Remember to put it into sheet 1. So technically speaking, I really should have made a copy of the trace analyzer, because by looking at the trace analyzer, someone can actually figure out the original source code. Okay, I'll tell you how it can be done, whether it can be done in time for turning in the homework assignment. Now that it is already 8:04. The answer is probably no, unless somebody already has the tool to do it. And since I have never talked about that tool, I don't think anyone has that tool, so I'm not too worried. All right, so the idea is these columns, okay, one of these columns is what is being loaded into the instruction register, or at least what is on the data port of RAM, and the other one is the program counter. So when you look at those two, you can actually look at the what we're looking at here, the trace of executing a program, and basically reconstruct at least a good portion of the program. You may not be able to reconstruct the entire program because the locations where the program does not execute, it's still not in the trace, and so you cannot really reconstitute that particular portion of a program. But the rest of the program actually can be reconstructed from sheet 1. Now the analysis tab, on the other hand, does not contain enough information to reconstitute the program, because it doesn't really tell you the opcode at location 01 in this case, and without the opcode you cannot reverse to the mnemonic of the instruction at location 01. Alright, so what we want to do, what I want to do, is to be super lazy, and we just go all the way to the end of the execution of this program where the halt instruction is going to stop, and it's right here. And we want to find out, we put the correct value into local variable x of main, and it's a 3. So let's check it out. Okay, so let's go back to the C code. We are trying to compute f of 4. So f of 0 is 0, f of 1 is 1, and so on. So let's go ahead and just do the hand calculation here instead of just looking it up. Okay, so f of 0 is 0, f of 1 is 1, f of 2 is f of 0 plus f of 1, which is 1, f of 3 is f of 2, which is 1, plus f of 1, which is also 1, so it's 2, f of 4 is f of 3, which is 2, plus f of 2, which is 1, so it is indeed a 3. Let's do f of 5 over here. F of 5 is 3 plus 2, so that's a 5, and then f of 6 is 5 plus 3, which is an 8. So we'll go ahead and try f of 6 next. Okay, so we just go here, and then we go to main. We change our test value, which was 4. So if I want to make the program a little bit more flexible, so I don't have to search through the code, we can always just say, test value is now 6. We want to test that. So we put, instead of using a constant of 4 here, I can now refer to test value as a label. So now if I want to change my program to test a different value, I just have one little label to change. Okay. So we'll go ahead and put this into the clipboard again. Actually, I really don't need to do that, do I? Well, because we can just go to here, go to the source. Usually I do not advise people to change the program. Okay, well, let's go ahead and change the whole program, because I also use a different label. I use a label instead of a constant. So we'll just go ahead and modify the whole program and make sure this is the correct one, because sometimes I make a change but then I forget to actually put the change in. So this is in fact the correct one. Okay, very good. So we go to RAM file. Well, truly only one location has changed between this one and the one last time, but to be sure, we can always just do this f.csv, overwrite or replace, go back to the command line, run it again. This time it should take a bit longer because we changed from f of 4 to f of 6, so it should take approximately 4 times the amount of time last time. And in Linux, there's a quick and easy command called time, and time doesn't tell you what the current time is. That's actually date. Time tells you how much time or execution time a particular program takes when you run it. So we say time, and it tells us that this time it took 5 seconds of user time, of which 2 seconds is real time. Okay, and if I ran the previous one, it would have taken about a quarter of the time. Okay, so it's still relatively fast. Then we go back to the trace analyzer, which is here, and take a look at what happens this time. So f file import upload and f.tsv, open it. Alright, so replace current sheet tab and no. Alright, and this time is, well, it doesn't take that long. I thought it would take a bit longer, and it's not taking that much longer. So what we want to look for is the halt instruction to be a 1. That's in column K. So if you search in column K for the value to change to 1, then you would have found the correct row. That makes it easier for you to kind of quickly locate the end of the trace. So let's see if we can do it this way. Okay, so we highlight column K and Control X to search, and we're finding a value of 1. And you can see how we are already searching within a specific range, and that's column K. So we just click find and say done. Oh, okay, I guess that is not the halt flag. Well, one of these has to be the halt flag, because, or maybe it doesn't have a capture because it's called halt. Okay, well, in that case, Okay, there's another quick way to do this. We go back to the assembler, go to the assemble tab, and find out what is the address of the halt instruction. So the halt instruction has an address of 46 in hexadecimal. So when we go to the trace, this time we have to go to the analysis tab because the other one only displays everything in binary. So now we go to column A, and then we look for, and again, I have forgotten what the value was. 46. Okay, so it's 46 in hexadecimal. So we find 46 within the range of column A, and say find. There we go. Done. Alright, so right here we can see that 8 is in fact stored to local variable x of main, and that's because f was actually put into register A earlier. And let's see where there's that. There we go. This is where register A got a value of 8, after the add instruction. So 2B, location 2B is probably corresponding to the add instruction in the assembler, and we can always confirm that. Okay, so we go to location 23, I think. Nope, it's not 23. It is location 2B. Okay, so location 2B is in fact the add instruction. So this is how we can kind of look at the trace and also the program, in the assembler, and just kind of understand how the program ran. All right. So I did mention a little bit earlier that I wanted you guys to use this program as a quote unquote somewhat of a study guide. Okay. So now the question is, what can you do to this program now that it is done? Unless you have a photographic memory, you're probably not going to remember the exact code that I wrote. So if you got a program but it didn't work, my suggestion is to continue to work on it even if it doesn't count for points anymore. But this is how you can study, because I have just talked about the concepts. Now that you have listen to the concepts, you can try to continue with your own program to get it to work. Okay, so that's one thing you can do. Okay, one suggested activity for those people who did not finish their own program. The second activity is really to look into the assembly code. Okay, and comment it. Just comment every single line of code and find out why it is there. Okay, what does it do? Why do we have to do this? And how does it relate to code that is either before or after that? Okay, so you want to analyze and comment this program the best you can so that you gain an understanding of what each line is doing. Okay, I think that is important. Okay, and the way you do this can be just using the text file, which is fine. Okay, but you can also do this in Google Doc. The reason why you might want to do this in Google Doc is because Google Doc allows you to draw pictures within the document. So if you want to display what the stack looks like, or if you want to display what is being pushed on the stack, why we have n, 1 plus, and so on and so forth, Google Doc is a better tool because it allows you to draw pictures and also write comment your own document if you want to. But regardless of how you do this, I think commenting this program to really understand how it works is really important. Now, statically commenting it is one thing. The other thing that you can also do is to go back to the trace analyzer. And I know someone is already screaming, no, not the trace analyzer again. Well, yes, the trace analyzer. So what you want to do is to capture your own trace, okay, and preferably not using a very large value for n. I would suggest maybe 2, because 2 is the one that will trigger the recursion, or maybe even 3, because that would trigger like at least 2 levels of recursion on one side of the recursion tree. So that will give you a trace when you will see the stack pointer going down and then back up and then back down again. Okay, and in that case, you can make a copy of the trace analyzer and then comment on the instructions that are special, that are interesting to you. So you can always use column F, G, H, I, and so on to write your own comments. So that becomes not really a general purpose trace analyzer anymore. It becomes your documentation of how this program works. Okay, and for that particular purpose, there's no need to stay in Google Sheet, because what you're doing is you're just looking at the spreadsheet as a big table, and as a result you can download it and then use LibreOffice or use Microsoft Office Excel as your tool for editing the result in the trace analyzer. So commenting the program is analyzing the program in a static way to understand how it works in a very static way. But if you want to know how the dynamic behavior, like what is happening on the stack, what is happening to the stack pointer, the return values, and so on, it is also helpful to look at the trace analyzer and document the trace analyzer as a way to quote unquote understand how this program works. So that's about it for this program. There's only one more thing that I want to kind of mention is when you approach a program like this, the best way to write this code is not really to write the entire program all at once. I talked about that on last Thursday already. So what you want to do is to test the program step by step. The halt instruction can be used for that purpose because it basically just stops the program at a certain point. So you want to test the program without recursion first. Okay, so you put a halt instruction right here, and then you test n with only either a 0 or 1 where it's not supposed to perform the recursion. So you have to get the program to work in that case first, because if the case where there's no recursion is not working properly, there's no chance the case with recursion is going to work. So there are ways to kind of work on this program step by step. That is not specific to assembly language programming. It has to do with how you analyze a program and then figure out a path of implementing features of that program in a step-by-step manner, so that each step is relatively small compared to the previous one, and it can be tested. So that is how you can tackle a more complex program in a way that in the end will save you time, even though when you're doing it, it would seem like it's wasting a lot of time because you're making small steps. But the point is, each small step is verifiable, so that you can say, okay, I know this program works at least up to this point, and I can count on that, instead of writing a whole bunch of lines where the program, you have no idea if the program doesn't work, why is it not working? Which is what I just did. Okay, I admit, I did not follow my own suggestion, but that's because I'm fairly familiar with this kind of programming already. Okay, all right. So this is the recorded portion where I will send to you guys, at 9 o'clock, because I don't want people to just copy and paste the answer at this point. So I'm gonna let you guys have this clip at 9, and that's it. Okay, I'm gonna stop the recording now.